That's what Peter did. He did calculus and physics as his both his electives.
That's awesome.
Yeah, that's a kid who's out to learn. All right. So starting discrete math now. Our first drill class, we'll get it recorded. These will be put up on YouTube. I sent you all links for the Facebook page via your email. So if you care about that, that's where that will go. And I'll keep updated there, all the updates, and that's where I'll also post homework solutions. Also hand out homework solutions in class when we go over it.
Do you want us to ask questions on there? Or just you?
Oh, yes. Ask questions on there and put a hashtag questions on it. That way you can quickly identify all the questions and make sure I get to them. But, yeah, we'll figure out how to use that as time goes on. Just put the questions there. Feel free to always text me and I'll say, just really quick, I'll repost this on Facebook and I'll answer the question. Or I'll probably just write the question myself and then answer it in the same thread. So, getting started now with discrete math. And discrete math, we're largely focused on deductive reasoning, but trying to give you a big picture for a second on how all these different bodies of knowledge tie together and where discrete math fits into all this. So, we briefly touched on this again. Let's briefly do it again, run you through it. So, talk about reasoning. What is reasoning? Reasoning is you justifying some conclusion that you've come to. You give the reason that you claim something. I think this because, and you state your reason. So your reason is your justification for accepting certain things as true. And there's three different types of ways that you can, roughly speaking, that you can justify something as being true. So, deductive reasoning, the typical example. If I tell you that Socrates is a man, and I tell you that all men are mortal, you're able to conclude that Socrates is mortal. This is your conclusion. This is the reason that you accept that as a true conclusion. And so this is reasoning here, and we call that deductive reasoning. Which is the type of reasoning that we're interested in this class. If this is true, then this is true. And notice that the truth of this whole if-then statement is what we call true in math. We never call this part true. We never call this part true. All we say in math is that if this is true, then this is true. That's how all mathematical statements that we call theorems are phrased. Look at something like the Pythagorean theorem. What does the Pythagorean theorem say? It says, if you have a right triangle, then the sums of the lengths of the legs squared is equal to the hypotenuse squared. It's an if-then statement. All theorems are phrased that way. And notice that while this may not be true and while this may not be true, the fact that this implies this is what's true. And that's true with capital T. To the extent that you can claim anything you know to be true as true, you have to accept that as true. And another thing to notice about this statement, we already quickly mentioned this, is you don't have to know about the particulars in the statement to know that the statement is true. You don't have to know who Socrates is, you don't have to know what man means, and you don't have to know what mortal means to know that the statement is true. I could rephrase this exact statement like this. If A is a B and all B are C, then A is a C. And it doesn't matter what A, B, and C are. Right? So that's deductive reasoning. Inductive reasoning is the reasoning of, that's the way that it's always happened, so that's the way it will always happen. That's the assumption. So when I let go of this marker, what's going to happen? It's going to fall. Do you know that it's going to fall with a capital K?
No.
Is that the only possibility?
No.
What else is possible?
It could flow.
It could flow. For all you know, I hollowed out the back, I stuck a piece of metal in there, I have a magnet up in the ceiling, and I fine-tuned it so that it's pulling upward exactly as much as gravity is pulling down on this thing, and the instant I let it go, it hovers. That's highly, highly, highly improbable, but still possible. Right? Or maybe the instant I let it go, there was some massive object in space flying through the air whose gravitational pull was the same on this, that the Earth is pulling down. That's possible. Highly improbable, but possible. So when we get to inductive reasoning, we're now in the realm of probabilities. And in all of science, we're using probabilities. When we say that something is a scientific fact, we do not mean that we know it like we know this statement. We mean that we are this % confident that it's true. That's what it means to know in science. In science, what it means to know in physics still isn't the same thing as what it means to know in biology. Physics is a low-level science. We can't call something true in physics unless we're 99.99999% sure. In biology, for it to be a biological fact, it only has to be true, I can't remember the percentage, but something like 95% of the time. So a biological fact is humans have 2 arms. Do all humans have 2 arms? No. That doesn't change the fact that it's a biological fact that humans have 2 arms. Right? Okay, so that is inductive reasoning. Now, can we, with inductive reasoning, ever know with capital K like we know these things are true? Maybe. So you've seen objects fall a lot, and so you can't say objects always fall this way. What if you saw it an infinite number of times, that when I let this go, it fell? Then could we conclude with capital K that this object will always fall? Yeah. An infinite number of examples. So that's what we need in inductive reasoning to get the same assurity that we have up here. If I give you infinite examples of a statement being true, then it becomes true. Then we know with capital K. For example, all numbers are even. Give you infinite examples. 2, 4, 6, 8. How many examples do you want? 10. All numbers are even. No! Not all numbers are even. Infinite examples is not enough. What if I prove to you that there's a 100% chance that it's true? Then do we know with capital K? 100%. Then do we know with capital K? Not 99.99999 rounding error 100%. 100%. Then do we know?
Yeah, we should.
The answer is still no. And we'll get into that when we get to probabilities and statistics. You'll understand it just fine because it's a calculus concept.
Okay.
Roughly, it's if I have a square, there's the area of a square, and I pick a random point, what's the odds I pick a particular point? 0%. And so the odds of not picking that point are 100%. Not 99.9999, it's 100%. You're using a limit there.
Yeah.
Anyways, so no, inductive reasoning is never as sure as deductive reasoning. It can't be. Infinite examples, not enough. Prove it's 100% of the time, not enough. All right. And then finally, we have the least reliable type of reasoning we call abductive reasoning. Roughly speaking, I don't want to get into a distinction between those too much for this class, but roughly speaking, it's the, I'll just say it. So inductive reasoning, you see a bunch of particular cases. Object falls, object falls, object falls, object falls. And then you create a generalization. So you measure this, you measure how it falls, you measure how it falls, you measure how it falls. First time you measure, it's 9.812 meters per second. Next time it's 9.814. Next time it's 9.809. And you keep measuring and it keeps falling, and it looks like it keeps falling roughly 9.81 meters per second squared. Right? So inductive reasoning, you see a bunch of particular cases and you generalize. Abductive reasoning, you take all your generalizations to reconstruct one particular case. Here you're using a bunch of cases to create a generalization. Here you're using all your generalizations that you created with this type of reasoning to reconstruct a particular case. So this is often the type of reasoning that we use in a history class. But I'll give you one example of abductive reasoning. Let's say you and your friend are walking down the street. It's a cloudy day. And as you're walking down the street, you feel a little bit of moisture on your hand. You've probably had this experience before. What's the conclusion?
It's raining.
It's raining. Now that's your conclusion. Now, of course, it's not necessarily raining. You're just using all your generalizations that you've created before to reconstruct that that's what's most likely happening. Because, for example, one of your generalizations are, it never rains if there's no clouds in the sky. So if there's clouds in the sky, that's still a possibility. You never feel rain unless you're outside. You're outside, so that's still a possibility, etc. And you're reconstructing what's most likely happening. But, of course, there's lots of possibilities. Maybe you're walking past someone's yard, they got sprinklers running, and one drop of their water happened to catch enough wind that it flew all the way and hit your hand. Or maybe your friend Pete had a particularly tough pee, and as he enunciated it, he got you a little bit, right? There's a lot of things that could have happened. So that's abductive reasoning. So here, really quick, to give you a sense of how these different fields tie together, the lower it is, the more fundamental it is. A field above presupposes a field below. What do we mean by that? So you have logic. In logic, we only use deductive reasoning. Then you have math. In math, what do? We essentially take axioms and we apply logic to those axioms and create definitions along the way. We prove things using logic and create definitions along the way. So in math, you can use logic. In logic, you cannot use math. Similarly, what do we do in science? We measure some generalization like this. Objects fall at 9.81 meters per second squared. We encode that in a mathematical model, and we start seeing the math that has to be true from that. And you'd see what that was like in a physics course. But that's what you do. You create some generalization, you encode it as a mathematical statement, then you start doing math with it. So in science, we can use math. In math, we're not allowed to use science. Similarly, in history, you can use science. If I'm trying to reconstruct when some particular dinosaur lived, I might use something like carbon dating. How exactly that works doesn't matter, but the point is, that's allowed. I can use science to reconstruct my history. I'm not allowed to use history to reconstruct my science. I can't say objects fall at 9.81 meters per second squared because when Julius Caesar crossed the Rubicon, he said so. Right? So that roughly helps you get a little bit of a picture of how all these things tie together. Now, obviously, what we're focused on is a math course. And since math presupposes logic, we're going to have to delve into logic a little bit to set up our foundations for our math. Make sense? Okay. And you already got a feel for the types of problems we'll be doing in this class. We gave you your homework problem. How many of you figured it out? None of you figured it out?
Not for certainty.
No, you would know if you got the right answer.
No, I didn't.
All right, so you were supposed to figure out a minus x times b minus x. Did any of you even write out the whole problem?
Not easy.
Wow, that's lazy. Times c minus x, you're in trouble. Because that's the first thing you need to do if you get stuck on a problem. Write it out. And we keep going. Eventually we get x minus x
Your problem was
times y minus x times z minus x.
Yeah, you had x before the letters.
Oh, was it x minus a?
X minus b.
All right, turns out it's not going to matter. We'll do this one.
I did not get what the ... meant.
Oh, you didn't?
No, I thought that was some kind of mathematical term.
It means continue the pattern.
Yeah, I
That's
figured
what ...
that
means. Okay. Yes, ... means continue the pattern, and hopefully you have enough information to know exactly what that pattern is.
The answer is 0.
The answer is 0! X minus x is 0. 0 times anything is 0.
You're right, writing it out would have helped.
Yes, it would have. Because chances are, as you wrote that term, if that was you writing the term, that's probably when the thought would have finally occurred to you. You would have wrote that thought. That's kind of weird. Isn't that just 0? Wait a second. And you're just multiplying? And yes, you come to the conclusion that it's 0. Now, that is meant to give you a taste for what problems are like in this class. See, taking this brute force trying to do it, no, not a chance. We're not going to work with 2 to the 26, 64 million terms. Expanding that out, that's insane. But, writing it out, seeing some trick, and realizing, oh, that's how you solve the problem, that's how problems in this class are often going to go. And now you know how to do this problem. It doesn't help you one lick for the next problem in the book. Because the next problem in the book is, here's a bunch of shapes, reorganize them in the shape of a square. And how does this help you do that? It doesn't. And that square shape problem has nothing to do with the next problem in the book. And that's how a lot of these problems are going to go. And so the only way that you can figure out how to do the problem is to sit there and think and think and think and figure out how to do the problem. There's no secret. There's no trick. There's just think about it. Once you see it, you see it. Until you don't see it, you got to keep trying. So that's why I'm so nice with you guys in this class in not making tests weighted so much. Because even if you knew everything we covered up to that point, I could still give you a problem on the test that you just can't figure out in the time that you're allotted. Maybe if you had enough time, you'd see it and you'd figure it out. Maybe not. You see? Okay. So that was that problem. All right. So we've already done sections 1 and sections 2 basically in this class, so now we're on to section 3. Section 3 is definitions, and section 4 is theorems. Basically, all of mathematics is creating definitions and proving theorems. That's the majority of mathematics. So let's go over which each of those are. Now, to remind you of the importance of definitions, we often ask the students, tell me one thing you know with capital K, and they often say something like, the sky is blue, right?
Yeah.
And then I pointed out to you guys, that is a very dangerous statement. Because you have no clue what this word means, and no clue what this word means, precisely. And so definitions are where we make those words very, very precise. So you already have a notion of what it means for a number to be even. But do you know exactly what it means for a number to be even? We need to be precise. So here's our definition of even. An integer is called even provided that it is divisible by 2. So now you perfectly know what even means, right? No. You should take issue with this definition. What's an integer? What's divisible? And if we're being really picky, what's 2? You need to know what integer, divisible, and 2 all mean for this definition to make any sense. And so we still need to define all those things. So what are the integers? Now we'll use this z with an extra line to represent the integers. You'll get used to it. There'll be a lot of notation that seems weird at first, but you'll get used to it. And so what are the integers? The integers are all the positive numbers following this pattern backwards and forwards. 0, negative 1, negative 2, negative 3, negative 4, negative 5, etc. Or 0, 1, 2, 3, 4, 5, etc. Those are all the integers. Make sense? All right. What does it mean to be divisible? Let's define that one. Let A and B be integers, so they're members of this set. We say that A is divisible by B, provided that there exists some integer C, such that B times C equals A. So A is divisible by B if B times some integer equals A. We also say that A divides B, or that A is a factor of B, and we write A divides B. Note, this is not divide as in division. We're not saying A divided by B. This is a completely separate idea. A divides B is going to be either true or false. A divided by B is a number. So for example, 2 divides 8. Is that true?
Yeah.
Yes. Does
Yes.
2 divide 8?
Yeah.
Is 2 a factor of 8? Does 2 divide 8?
Meaning that it turns into an integer? Or that
2 is an integer, 8 is an integer. Does 2 divide 8?
Yeah.
Yes. How do you know?
2 divided by 8 is a quarter?
No. Nothing to do with division. Look back at our definition.
Because 8 times.
Let A and B be integers. We say that A is divisible by B, or in other words that, oh, I've got it backwards here, don't I? If A is divisible by B, then we're saying B divides A. Shoot. I should have written it like this. Got my order here backwards, which is probably what's throwing you off. B divides A.
Oh.
Sorry.
Oh, okay.
Sorry about that. Okay. I think I understand your confusion. Now we're good. Does 2 divide 8?
Yes.
Does B divide A? How do I know when B divides A?
If
When there's
C times
something-
3,
When we can find some integer C such that B times C equals A. Can we find some integer such that 2 times that integer equals 8?
Yeah.
What?
4.
4. That's how you prove it. Does 2 divide 8? Yes.
4.
How do we justify it? Because 2 times 4 equals 8. So 2 divides 8 is true. This is a statement. This is something that's either true or false. 2 divided by 8 is an operation. That takes numbers and it spits out numbers. 2 divided by 8 is 1/4. This is in no way the same thing as this. Very different things. Students get super confused by that in this class because similar language. Don't get confused by that. 2 divides 8 is a statement. It's either true or false. 2 divided by 8 is a number. Okay, let's do some examples. Does 4 divide 8?
Yeah.
Yes.
How do you know?
Because 4 times 2 equals 8.
Perfect. Does 8 divide 12?
No.
3 halves.
That's
8
not
times
an
3
integer.
halves equals... That's not an integer. Good. 3. Does 3 divide 5?
No.
Does 27 divide 3?
No.
9.
Yeah, negative 9.
Yeah, negative 9 times 27 gets 3.
That'd be 1 9.
All right.
No.
So no. Does 0 divide 1?
No.
0 times 10 million gets you
0.
Oh, still not 1 yet? Maybe 0 times 20 million. Okay, does 1 divide 0?
Yes.
Times 0.
1 times 0 equals 0.
1 times 0 equals 0. 0 is an integer. It's right there. Can I find something in here such that 1 times something in here gives me 0? Yes, it's that one. Make sense?
Yep.
Making reference to these definitions. Okay, now we still have a problem. We've been using things like 0, 1, 2, -1, -2. We didn't define those things, right? And we could define those things.
It's true.
We're not going to in this class, but just to give you a quick example, the exact definition of 2 using set theory, 2 is defined to be the set this. And there's no reason that this should make any sense to you. But there you go. There's 2. That's its exact definition. And it would be a whole class in and of itself, starting with basic logic and building up all these numbers and defining 0, 1, 2, etc. And defining things like plus, subtraction, multiplication, division, less than, greater than. We're going to take these things for granted in this class. We don't have time to start from the ground up. That would take up the whole class. So we're starting here and continuing on. So I'm going to assume that you already know what numbers are. And we're not going to define any numbers. And we're not going to define any of the arithmetic operations. Plus, minus, multiply, divide. We'll assume that you're good with those. Less than, greater than. We'll assume you're good with those. Outside of that, everything else we use in this class, we'll define it as we go and build up with it.
Are we going into set theory?
We will come back to set theory, but we will not approach set theory as a foundations to all of math in this class. Okay, so there we go. So now when we come back here and we read, an integer is called even provided that it is divisible by 2. Now we know what that means. We now know what divisible means, right?
Mm-hmm.
We now know what an integer is, it's these numbers, and we already assume that you know what each individual number is, so we won't bother defining things like 2. Good? Any questions with that so far? Okay, so let's run a couple more definitions. What does it mean to be odd? It means it's not even, right?
That's right.
Is pi even? 3.14159 da 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 da. Oh, so it's odd.
Naturally.
Okay, so odd isn't just not even. So that's not a definition of odd.
An integer is
So what is pi?
What is pi? Pi is the ratio of the diameter of a circle to its circumference.
No, like what is like?
That is its definition. 3.14159 blah 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 blah. That's a numeric approximation. That's not pi. Pi is the ratio of a circle's circumference to its diameter. That's its definition, and that's where you should start a trig class. But that's not where they started, for some reason. Anyways, so what do we mean by odd? Here's exactly what we mean by odd. We'll make it very clear. An integer a is called odd, provided that, now again to throw a bunch of notation at you that you just got to get used to in this class. So an integer a is called odd, provided that there exists
An integer.
x in z, or an integer, perfect. Have you seen this notation before?
Yeah.
Have you?
We were in your, we started your class.
Okay. Well, that's great. You'll get refreshed on this. Once you get it, it'll be easy enough, but yeah. Usually the first time you throw this stuff at kids, it's like, whoa. Alright, so yeah, there exists x in, that means is a member of z. So x is in here. So there exists, we can basically read that as an integer x, such that a is equal to 2x plus 1. If I can find some number x such that 2x plus 1 is equal to a, then a is odd. That's the definition of odd.
Why can't you just do not an integer that's not even?
So you could do that, and that would be something that we say is logically equivalent. And we will prove in this class that those are logically equivalent. We will prove that every integer is either even or odd, and that every integer that's even is not odd, and that every integer that's odd is not even. And those will be things that we prove. But notice that if this is our definition of odd, then it gives us a mathematical way of expressing that number instantly. Notice just saying that it's not even, that doesn't give us the formula to represent it with. So it's a harder definition to work with. It would work, just be harder to work with. Anyways, so here's our definition. So 19, is that odd?
Yeah.
How do you know? What's the magic number?
What's
the
9.
x?
9.
9. We know that 19 is odd because 2 times 9 plus 1 is equal to 19. If we can find some integer such that 2 times that integer plus 1 gives us our number's odd. Give me example 1 that you can't do. 4. 4 is equal to 2 times, what's the magic number I put there, and plus 1, 2 to get 4? What's the integer I put there?
1.
If I put 1 there, we get 3.
Oh.
If I put 2 there, we get 5.
That's even. You can't do that.
You can't do it. Because 4 isn't odd. Only odd integers can be expressed this way. It's a definition of odd. Right? Okay. So 57. Is that odd?
That's odd.
Yeah.
How do you know?
23.
18.
33. 23. 30. No,
26.
26. 27. 26.
18.
27.
Back up. What is wrong with you? What is 2 times 28?
It ends with 6.
46.
Oh, yeah.
56.
I said that.
56 plus 1.
Who said 28?
I said
He said a lot of numbers.
But 28 was in there.
You can't just sit there. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17.
Technically, you got it.
Is there a limit on our tries?
Alright, so it's 2 times 26 plus 1. Come on, use your brain a little bit. You just had to subtract 1 from that number and divide it by 2. What's 57 minus 1?
56.
56 divided by 2. It's half of 56.
28. 28. Why are you writing?
Alright, you guys.
Wait, why'd you write 26?
Oh, I don't know why I wrote that. That's why you guys were saying 26. I wonder why you kept saying that. 56, how do you divide by 2? What's half of 50?
25.
What's half of 6?
3.
Put them together.
28.
There you go. 26, right? Okay. 1 is 1 odd.
Yeah.
Yes.
What's the integer?
0.
2 times 0 plus 1 equals 1. Wonderful. 11, is that odd?
Yeah.
What's the integer?
5.
5. 2 times 5 plus 1 is 11. Negative 11, is that odd?
Yeah.
Negative 6.
Yes.
Oh no, we're two.
I'm right.
No. No, you're not.
Yes,
2 times negative 6 plus 1 equals what?
11. Negative 11.
Yeah.
Negative 11.
Yeah, you're right. Wow.
He is right.
That's what I was saying the whole time.
So notice, the integer that you expect when it's an odd number is 1 less than what your intuition might tell you. Right? And then finally, negative 57. What's the number?
Negative 29.
Negative 29. That was some quick thinking. Did you just do 1 off of 28? 2 times negative 29 gives us negative 58 plus 1 gives us negative 57.
You just added 1 and then divided by 2.
Subtract 1.
That's what I said.
Alright, so there we go. I think you now know what even and odds are. Making some good progress here, right?
Yeah.
Be sure to go tell your elementary siblings, I now know what an even and an odd is. And watch them laugh at you. Alright, next, prime. An integer p is called prime, provided that p is greater than 1, and that the only positive divisors of p are 1 and p. In other words, the only positive integers p is divisible by are 1 and p. That's what it means to be prime.
So 3.
3 is an example. 2 is an example. 7 is an example.
Why can't you have a negative prime number?
Because then there'd be more.
Because by definition, it's not prime.
Go.
We're not saying, let's come up with words that happen to describe all prime numbers. We are saying, here's the definition of prime.
Okay, so they're just not negative because of.
By definition.
Yeah.
Yeah.
Someone chose that because it does.
Yes, all these definitions are somewhat arbitrary. Someone decided that that way of thinking about something is useful. Why is even such a great definition? Someone thought it was useful. We have a special word for integers that are divisible by 2. Why don't we just always say divisible by 2, divisible by 2? Notice that you never in math actually need a definition. It just makes communication easier. I never have to use the word even. I could always just say divisible by 2. I never have to use the word odd. I could always say is expressible as 2 times some integer plus 1. Becomes a mouthful. The point of definitions, just like in a dictionary, the definition of a word equals all these words. It's a shorthand way for expressing a more complex idea. Same thing in mathematics. All definitions, they're just expressing more complex words in fewer words. You go back to, you did college algebra, right? And so you remember in that class what we had as like our definition of 10. Right?
1 plus 1 plus 1.
Right, and so this is a much shorter way to write that.
Yeah.
So all definitions are somewhat arbitrary. You don't need them to do math. They're just useful. They help you say things that would otherwise be hard to say in fewer words. Communicate the ideas clearly. So that's all definitions do. Okay, so we got a prime. Let's get now a composite. What's composite? A positive integer a is composite, provided that there exists some integer b such that b divides a, and b is in between 1 and a. So is 9 prime?
No.
No. Is it composite?
Yes.
How do you know it's composite?
The C for B divides A is 3.
Because of 3. 3 divides 9, and 3 is between 1 and 9. That's how you know 9 is composite.
I see.
Is 7 composite?
Is what?
Is 7 composite?
7. No.
No. What are the positive integers that divide 7?
1 and 7.
Just 1 and 7, right? Is 1 between 1 and 7?
No.
No. Is 7 between 1 and 7? So there is no integer that divides 7 and is between 1 and 7. So 7 is not composite. So it's prime. Right? Alright. So here's a bunch of numbers. You're just going to tell me prime or composite. 3, prime or composite? Prime. 11, prime or composite? Prime. 15, prime or composite?
Composite.
Composite. How do you know?
5.
Because
You mean
there
3.
exists a number 3 such that 3
Both
divides.
5 and 3 work, right? They're not saying there's one and only one thing that divides it. They're just saying there's something that divides it. If there's any integer that divides it, that's between 1 and the number itself, it's composite.
There has to be at least 2, doesn't there?
There's always going to be at least 2.
Yeah.
If there's 1, then there's at least 2. Yeah. But all we care about is there's at least 1. All right. 8.
2 and 4. So
Composite.
Composite, yeah.
And 2 and 4. 4.
Composite.
Composite.
Composite. 2.
Prime.
It's even.
That don't matter.
That don't matter. Even doesn't show up anywhere in those definitions. Wonderful. It's prime. 1.
Prime.
I'm gonna yell.
1/2 times.
Is
2.
1 prime?
Yes.
No!
Why?
P has to be
Look at your definitions. Stop relying on your intuition. Your intuition is garbage. Get that clear. And this is on the simple stuff. So this is one of the biggest mistakes students have when they first start doing rigorous math. You rely on your intuition rather than double checking with the exact definition. Look back to the definition. All right, 97.
Prime.
Not sure? It's prime. -7.
Prime. I mean,
Not prime. Composite.
Prime, not composite?
Not anything, just not.
Neither!
composite. Wait.
Wonderful! In order for it to be prime, it has to be.
Greater than positive.
In order for it to be composite, it has to be.
Positive. Positive.
So -7 is prime.
Nothing.
No.
No! There we go. 16.
It's
Composite.
-16.
Nothing.
No.
Wonderful. You're getting these down. Okay, so those are the basic definitions we'll be starting out with in this class. Not too bad, right? All words that you've seen before, but now precisely defined. And you now finally know what it means to be prime, and what it means to be composite, and what it means to be even, and what it means to be odd. And you can go brag about that to your siblings. Okay, so now we move on to the next section. So section 3 was on definitions, section 4 now is on theorems. I told you basically all the mathematics is just definitions and theorems. Definitions are what we've been doing here. Theorems are things like this. Theorems are, if this is true, then this is true. We prove that if this is true, then this is true. We prove the whole thing. the whole statement is true, and that is what a theorem is, like the Pythagorean theorem. If you have a right triangle, label the sides A, B, and C, then a squared plus b squared equals c squared, right? And so it's for proving theorems. When you're proving theorems, that's when you need to use logic. You don't really have to use logic in coming up with definitions. It's in using theorems that you need logic. So now we're going to jump into the logic part of today's class, which is section 4. We'll be doing a much deeper dive than the book does, just because I want to give you good foundations. So it will seem like what we cover in class is kind of complex, but then when you go back and look at your homework, it's going to be really simple compared to what we covered in class. Does that make sense? And hopefully we can, well, I don't need that on these tables. It's those other tables that shake so bad. You want to get the front bank of lights. If I remember right, this shows up better on the chalkboard than it does on the whiteboard. Yeah, should have just left it. Okay. Marker. Chalk. Okay. So logic, we'll be covering propositional logic. Don't need that, we've already covered that. So in logic and all of math, what we are interested in are statements. Things that we can call true or false. When you're proving something, you're proving it's true. Or when you're disproving it, you're proving it's false. And so what we're talking about there are statements. So what is a statement? Statement. A statement is a sentence that is either true or false, but not both. Pretty straightforward? All right, notation. We typically use the Greek letters alpha and beta to represent statements. So when you see alpha and beta, you can pretty much assume we're talking about a statement. Let's do some examples. Which of the following are statements? Go back home.
No, it's not a statement.
Is it true or false? Doesn't make sense because it's not a statement. 2 times 2 equals 5. That's false, so not a statement.
No, it's a statement.
You think that's true?
It doesn't have to be true to be
Ah, you think it's false. Still a statement. Wonderful, don't get confused. Not a statement is a statement. 2 times 2 equals 4. Is a statement. New York is a suburb of Los Angeles.
Statement.
It is a statement.
That's not true.
Yeah, it doesn't.
Ah, it's false. Thursday up tar paper.
That's a statement
That's
for sure.
definitely a statement. That's true.
Alright. False. Not a statement. The silliness is speedily.
Not a statement.
Not a statement. I am the most beautiful girl in town.
It's true.
True.
I mean,
True.
statement.
And if you can call it true, it's a statement.
True.
X plus 2 equals 5.
Not a statement.
Not a statement.
Unless you know what X is.
Because you can't, right, it depends on what X is to call this true or false.
A proposition.
Like if it
Wonderful.
was silliness and speedily.
Not a proposition. The other one. Proposition and statement are the same thing.
Oh,
This is what we call a predicate.
predicate. That's
But we won't be bothering with predicates in this class. Well, we will eventually. But we're not going to do predicate logic right now, so. Yeah, this is not a statement, because it depends on what X is. Alright. So, good start there. Now, we can take existing statements and we can, let me just read what we have here. We can construct new statements by combining existing statements. So we had one statement from the previous slide. New York is a suburb of Los Angeles. We had another statement from the previous slide. I am the most beautiful girl in town. We can combine those with the word and we call that the conjunction. We are not using conjunction the same way that we did in English. And is the only conjunction in logic. So we constructed this new statement now. New York is a suburb of Los Angeles, and I am the most beautiful girl in town. Right? So that's what we mean by conjunction. If alpha and beta are statements, the statement alpha and beta is called the conjunction of alpha and beta. Right?
Yep.
Now, is this a good definition?
You don't know.
Are we missing something here? It's your intuition that makes you not want to say yes. But yes, we are missing something. I just randomly called alpha and beta a statement. I'm just assuming, since alpha is either true or false and beta is either true or false, then alpha and beta is either true or false. But how do we know that?
Truth tables.
We need a truth table. So, your intuition is telling you, if you know that alpha is true or false, and you know that beta is true or false, then you know that alpha and beta all taken together is true or false. And your intuition is telling you that. But now we need a truth table to help us define how to AND these things together. So notation, we write alpha and beta as alpha and beta. You'll use that notation as the class goes on.
And the V means not.
Or.
The V means or. The not is almost like a negative sign. So how do we define these things with the truth table? So if here's alpha, here's beta, here's alpha and beta. Notice that each of these we're claiming are statements, right? Now alpha I already told you is a statement, and beta I already told you is a statement. That was given. So alpha has to be true or false, beta has to be true or false. So all our possible combinations of alpha and beta are what? We can have alpha is true and beta is true. We can have alpha is true and beta is false. We can have alpha is false and beta is true. We can have alpha is false and beta is false. And if this is really a statement, and I wasn't lying to you, then we should be able to see if this is always true or false.
Okay.
So we know no matter what alpha and beta are, they're one of these four combinations because they were statements. We're arguing that this is also a statement, which means it has to be true or false in any possible scenario. So we need to check that. So if alpha is true and beta is true, then alpha and beta is true. If alpha is true and beta is false, then alpha and beta is
False.
True.
False.
Oh, false. Yeah.
Ding dong.
Yeah.
Let's get a marker and chalk. We'll make alpha is Donnie's holding chalk. We'll make beta Donnie's holding a marker. Right? Let's set up this scenario. I'm holding a chalk is true. I'm holding a marker is false. I'm holding a chalk and I'm holding a marker.
False.
False. Alright? So that's the next scenario. I'm holding a marker and I'm holding a chalk.
False.
False. I'm holding a marker and I'm holding a chalk.
You're after
It's
false.
true.
False.
Why is it not true?
But two negatives.
I'm holding a marker and I'm holding a piece of chalk. Is that true?
Okay, but it's true that they're both false.
You're overthinking it. Just listen to the statement. I'm holding a marker and I'm holding a piece of chalk. Is that true? Now, so false and false is false.
That's true.
And yeah, you'll overthink these at first, but once you get used to them, you'll get used to them. Plain and simple. So while we used the way that we use English words to figure out the values here, really this is a definition of what we mean by the word and. Here's this definition. So that would actually be how we define it in a logic course, but that's not what we're doing here. We're just making sure you understand what ANDing is. So there we go. Okay. Now that was for the word and I said that and is the only conjunction that we have in logic. You've studied English, and you know there's other conjunctions. There's words like the word but. Do we have the word but in logic? And the answer is no, we don't have the word but. And let's make clear why we don't. So, I love you is a statement. I love your brother is a statement. So when I add those together, I love you and I love your brother, that's still a statement. If I say I love you and I love your brother, you know exactly what I'm saying. I'm saying that this statement is true, and I'm saying that this statement is true, and that's exactly what I'm saying. Now let's replace that and with a but. If I say, I love you, but I love your brother, or some pretty girl says this to you, then what are they saying? Are they saying that they love you? Are they saying this is true? Yeah. Are they saying that they love your brother? Are they saying that's true? Yeah, so they're kind of saying the same thing. They're saying this is true and they're saying this is true, but they're saying something slightly different as well. Are these two statements saying the exact same thing? No, this but somehow implies that there's some other connection between these two things. What precisely is a connection? You can't precisely say it. It can't be precise.
The right side just a little bit more true.
You're guessing from context, and what does it mean to be more true in logic? There's just true and false. You see? And so there's some subtlety there in the English language that cannot be perfectly defined. You cannot perfectly define what this word means. It's a piece of English that is inherently ambiguous. If you're writing a poem, it's much better to use this word than it is to use this word. There's more ambiguity, more room for interpretation. In logic, we can only use completely precise language. You have to know exactly what I'm saying. Here, we can determine exactly what you're saying, given that we understand this sentence and this sentence. Here, even if I perfectly understand this and I perfectly understand this, perfectly understanding the whole statement? Impossible. Not really hard, impossible. You get great intuition for it as a human being, and obviously that's good enough. But if I were to tell you, make it precise exactly what it means, you can't do it. That's the problem. And so in English, we're only interested in those parts of, or in logic, we're only interested in those parts of language that are completely unambiguous, and those are the pieces of language that we're going to use in our proofs. Now, you don't need to be so careful in your proofs that you only ever use the word and you never use the word but. That's a bit rigorous. We won't bother with that. Just giving you an example of why the logic words are the words that we use. So in logic, we're only interested in the univocal parts of language. Univocal meaning it can only be interpreted one and only one way. Equivocal means it can be interpreted in many ways.
Did you say equivocal?
Equivocal,
Okay.
many interpretations. Univocal, only one interpretation.
Okay.
Okay. So, mouthful here, to give you a feel for logic. In terms of sentential connectives. What's a sentential connective? It's a thing that you connect onto a sentence. And is an example of a sentential connective. I could take two sentences and I can and them together. If alpha is a statement, Jack believes is a sentential connective. Give me any statement, I can add Jack believes to it, and it gives me a new sentence. So what's a sentential connective? It's things you can add onto sentences to get new sentences. So in terms of, and all the operations we talk about in logic are going to be sentential connectives, things that you add onto statements. So in terms of sentential connectives, the terms or phrases you can connect onto statements in meaningful ways. We are only interested in the ones that are truth functional. Or in other words, the truth or falsity of the resulting statement can be completely determined from the truth or falsity of the component statements. What do we mean by that? So, and we showed was truth functional. Because if I told you that alpha is true or false, and I told you that beta is true or false, you could tell me whether alpha and beta is true or false. If I told you alpha is true and beta is false, then alpha and beta is false. And you can determine that. It's truth functional. That's what it means to be truth functional. It means if I told you the truth or falsity of the component sentences, you can determine the truth or falsity of the whole sentence. Right? Now I tell you alpha is true. So alpha is true right now. Now I tell you Jack believes alpha. Is that true or false?
It is true or false. You just somehow
You can't determine it. I don't know what Jack believes. And just because alpha is true doesn't necessarily mean Jack believes it's true. Just because alpha is false doesn't necessarily mean Jack believes it's false. So this is not truth functional. Jack believes is not a truth functional connective. Because if you know the value of alpha, you cannot determine whether Jack believes alpha is true or false. And what's truth functional? Because if you knew the values of alpha and beta, you could determine the value of the whole thing.
So Jack believes supposed to be beta, or Jack beta?
Jack believes is like and. It's something that we added onto a sentence. Let's do a couple more examples and I think you'll get it. So, let's say that alpha is true. You with me?
Okay.
It is not true that alpha. Is this whole thing true or false?
It's false.
It's false. Notice how you were able to determine that. What if alpha were false? Then it is not true that alpha is
False. Or true.
true. Notice how you were able to, if I tell you whether alpha is true or false, you're able to determine if this whole thing is true or false. Here we weren't able to do it. So this is not truth functional. This, it is not true that, is a truth functional sentential connective. And it might make sense to somehow wrap this up in logic. And it is not true that, or it is not the case that, is usually what we mean by not. And so we'll end up encoding that with
Why
a simple
can't
not.
we figure out Jack believes then if we can just say Jack believes is false and A is true? Then the whole thing is false.
No. If I tell you what alpha is, can you tell me that the whole sentence Jack believes alpha is true or false?
It depends on what Jack believes is.
Right.
There's no beta. If Jack believes
It-
is true or false.
Right. Jack believes is not truth functional.
How is it any different from it is not true that? You can name it is
Look.
not true that false.
Let alpha be the sky is blue.
Okay.
True or false? Jack believes that the sky is blue. True or false?
It depends on what
You can't answer the question. Now come down here. The sky is blue. It is not true that the sky is blue. True or false?
Yeah, it's false. Okay.
you were able to figure it out. So here you can figure it out just by knowing what alpha is. In other words, this whole thing right here is a function of alpha. That's what it means to be truth functional. This is not a function of alpha. Even if you know alpha, you still can't determine the value. This, if you know alpha, you can determine the value. All right, next one. Alpha and beta. Is that truth functional? If you know alpha and you know beta, can you determine the truth or falsity of alpha and beta?
Yeah.
Yeah. If alpha is true and beta is false, then alpha and beta is false. Finally, it is probable that beta.
Kind of.
If you know beta, can you figure out the truth or falsity of the statement?
Yeah.
No.
Like what? Oh. Yeah. Okay.
It's either 100% or 0%.
Beta is it? Beta is Jeremy won the lottery. It is probable that Jeremy won the lottery.
Is beta true or false?
You can't.
Let's say that you did win the lottery. That doesn't make what you did probable.
True.
It happened to happen. Right?
Yeah.
Okay. So in logic, we're interested in these types of truth functional connectives. We're interested in ones that are truth functional. In other words, you can determine if they're true or false, given whether or not their components are true or false. And secondly, we want them to be completely unambiguous what they mean. So those are the two things we're looking for with our logical notation. All right, so we got the word and that was nice. So we have one word so far. Can we get another word that we're going to add to our logic vocabulary? Or will be the next one. And we call that the disjunction. So if alpha and beta are statements, the statement alpha or beta is called the disjunction of alpha and beta. And it is false if both alpha and beta are false, otherwise it's true. Notation, we write alpha or beta as alpha or beta. Notice that and or use the same symbol, just upside down from each other. So let's draw the truth table for or, make sure we understand it. Here's alpha, here's beta, here's alpha or beta. All the possible combinations, we could have alpha's false, beta's false. We can have alpha's true, beta's false. We can have alpha's true, beta's true. We can have alpha's false, beta's true. Give them to you in a random order so you're not just memorizing orders. All right. So now, false or false is
False.
false, right? True or false is
True.
good.
Yeah.
True or true is
True.
true. And false or true is
True.
wonderful. So you guys already got that one down pretty easy. Because it is false if both alpha and beta are false, otherwise it's true. So this is the only case where it's false, by definition. Now, in English we use this word or, and we use this word or in two different ways. Give you an example of the two ways that we use the word or. If I said to take this class you have to take geometry or algebra 2, if you took both geometry and algebra 2, can you still take my class? Yes. Now let's say you order a steak, and I say that comes with soup or salad. Do you get both the soup and the salad? No. So in one of those ways I used it in English, both cases was fine, we still accepted that as true. In the other case, both of them we didn't accept, right? So the soup or salad one, when we say it that way, we mean the exclusive or. Oh, I guess I have examples right here. Now in English we use or in two ways. Inclusive, you must take physics or calculus to apply for my class. Inclusive or, you can take both physics and calculus and that's okay. So true, true is true. The exclusive or, that order comes with the side of salad or soup. They're using that in the exclusive sense. You can have salad and not soup, or you can have soup and not salad. Right? And then note, if we want to use the exclusive or, we write it this way, or that's a symbol. But you'll never really see that again. So in logic, we always mean or this way, and this is the way we always use it. Any questions on those?
No.
Okay, next, negation. So if alpha is a statement, the statement alpha is false, or it is not the case that alpha, the statement alpha is false is called the negation of alpha. We also say not alpha to negate it. Notation, we write not alpha as that symbol, not alpha. Let's write the truth table for this, just to make sure we got it. So alpha, what are all the possible combinations for alpha?
True, true, false, false.
True, false.
Alpha can be true, true, and true, false.
Wait,
What? Yeah, that
I was
doesn't make
going
sense.
down. I was going
Just
true,
true,
false,
false.
true, false, or true, true, false.
No, it's just
Just
true.
Alpha can be true or false.
Right.
Before we had two variables, so there were four possible combinations.
I see.
If you only have one variable, just two possible combinations, it could be true or false. So now we're trying to figure out the value of not alpha. If alpha is true, not alpha is
False.
false. If alpha is false, not alpha is
True.
true. Now this one seems like the simplest of the logic operations, but it's actually one of the most subtle and sometimes one of the most confusing. It applies as the most confusing. This is the second most. So let's make sure that we understand it. If alpha is true, not alpha has to be false. It sounds like what I'm saying is really obvious, but sometimes it's hard for this to click. Alpha, not alpha, has to be saying the exact opposite thing as alpha. Maybe examples, and we'll come back to why this is kind of tricky. Because otherwise you'll feel like I'm just saying the same thing over and over again. All right, so note, not alpha is a contradiction of alpha. We always know that either alpha is true and not alpha is false, or that alpha is false and not alpha is true. Has to be one of those two cases. For any statement alpha, either alpha is true or not alpha is
So
true.
you can have multiple.
One of those always has to be the case.
You can have multiple not alphas to one alpha.
No. Yeah, so I see why you're saying that. So yeah, we'll get clear with that with some examples. So which of the following are negations of all swans are white? Some swans are black.
That's a negation.
Nope,
That's a negation, right?
it's not.
No!
Negation.
This is why not is so confusing. What is the opposite of all swans are white? So let me give you an example. Imagine that you live in a universe where every swan is yellow.
Okay.
Right? Possible universe, right? Is it true that all swans are white?
No.
Is it true that some swans are black?
No.
Then these can't be negations of each other. Because if alpha is true, then not alpha has to be false. And if alpha is false, then not alpha has to be true. So if this is our statement alpha,
Okay.
this is not alpha. This is not an example of not alpha. This is not a negation of this.
But it still proves that wrong, right?
Because this is not false every time this is true, and this is not true every time this is false.
I see. But it is.
These happen to be what we call contrary
It
statements.
is false every time it's true, but it's not true every time that one's false.
Right, so they're not contradictions of each other. If they can't both be true, we call those contrary statements. Contradicting statements are one and only one of those are true, and one and only one of those are false. These are not contradicting statements. So this is not the negation of this. Let's continue. At least one swan is black.
That's not That's not.
This is not the contradiction of this. They're contrary statements. They can't both be true. So that's not the same thing as contradiction. All right, some swans are not white.
Contradiction.
There's our contradiction. Pick any universe you want. Let's say we live in a universe of yellow swans. Is it true that all swans are white?
No.
Is it true that some swans are not white?
Yes.
Notice that if this is false, this has to be true.
Then
And
you,
that if this is false, this has to be true.
you could also put in that all swans are not white. And that would also be a contradiction.
So you want to say all swans are not white. Let's look at that one. Imagine that we live in a universe where half our swans are white, half our swans are black. Is this true?
Huh.
Oh, then this has to be true. Oh, wait. So this is not the contradiction of this.
So you have to contradict the R and the all.
We won't worry about that right now. The point is just to wrap your head around negation. To point out why it's trickier than you think. All right? Finally, not all swans are white. Oh,
Negation.
this is a negation of this, right?
Literally.
This is all swans are white. This is not all swans are white. Imagine you live in a universe where half your swans are white, half are black. Are all swans white?
No.
So not all swans are white?
Yes. So some and not all are the same thing. Mean the same thing.
No.
Oh, there's also not, yeah.
Yeah.
So
Look.
there's two of the same one.
Here's what you're trying to get at. I'll just give it to you since you've probably seen the symbols before. Not for all x, some proposition about x is the same thing as there exists x such that not that proposition about x. And you've probably seen that. That's the distribution. So not all is the same as there exists not. Okay. And we'll learn about more of that later. For those of you who haven't seen this before, don't worry about it. We'll get there. Okay. Every swan is not white.
That's not much.
Is that a negation of that statement?
That's the one I brought up.
Every swan is not white. All swans are white. Let's imagine a hypothetical universe. Half our swans are white, half our swans are black. Are all swans white?
No.
Right, okay.
Then every swan is not white.
No.
No. Wonderful. Okay, so negation. If alpha is true, the reason that negation is so useful is because then if you know some statement's false, you instantly know its negation is true. That's why this is so crucial. And so you have to be able to figure out what its negation is. If I tell you all swans are white is false, you need to instantly know what you can conclude from that. You can instantly conclude this. Some swans are not white, or you can conclude not all swans are white. These are the only two things you can conclude from knowing that that's false. Make sense? That's why it's so useful. Okay, so there's negation. One that's subtly trickier than you expect it to be. What the? Did I not go to the next one? All right. So let's see some more with negation and how it gets sometimes trickier than you think. Negate each conjunction. So let's try it. Today is Monday and the weather is cold. How would we negate that? Tell me the opposite of that statement.
Today isn't Monday or the weather isn't cold. Not today's Monday, the weather's cold.
Today's not Monday and the weather is cold? Is that the negation?
Today is not Monday.
Not today's
and
Monday.
the weather is not
Or
cold.
the weather.
Today is not Monday and the weather is not cold.
Oh yeah, you switched it.
Or.
The and to or. Today isn't Monday or the weather isn't cold.
All right.
That sounds
So the correct way is what Jeremy was saying already. So today is not Monday or the weather is not cold.
I get it.
And here's trying to help your intuition. So today is Monday and the weather is not cold. How could we make this statement false?
Today is not Monday and the weather is
How could we make sure that this statement right here, today is Monday and the weather is cold, right? When can that statement be false? It can be false if today is not Monday, right? That makes it false. Or if the weather is not cold, then it's false. And notice that I just said this same thing right here.
Yeah.
Make sense?
Yeah.
It's weird until it clicks with your intuition, then it's not weird. Good?
Yeah.
Let's try another one. All cats are black and all men are mortal.
Not all cats are black or not all men are mortal.
Perfect. You said the easy way. Another way to say it is some cats are not black or some cats are not mortal. Or some men are not mortal. But perfect. You can say exactly how he did. Not all cats are black or not all men are mortal. Works perfect. Right?
Or couldn't you say, or some men are immortal?
Well, now you're just trying to use the opposite of mortal.
Right.
But you still have to be careful about just flipping words and see if that works the way that you think. Is a rock mortal? No. So it's immortal? No. Doesn't live. So sometimes taking opposites like that don't really work out the way you expect. And maybe that's actually something worth bringing up with negation versus opposite. Because this is one that students also always get confused on. What's the opposite of black?
White.
White. If I tell you a color's not black, then it must be
White.
white, right?
No.
No. So opposite and negation, not always what you think. Sometimes your intuition's right, sometimes your intuition's not right. So be a little bit careful just thinking opposite. All right, next one. Some rectangles are squares and some triangles are equilateral. We're trying to negate that. When is this false?
When some rectangles are not squares, and some
Or some triangles are not equilateral. Right? Or we could say, well, we won't.
That
say it
doesn't
that way.
negate it.
Yeah, it does.
There can still be some square and some not square.
When there
Some
exists.
doesn't negate some.
Oh,
It's gotta
right.
be all.
Thank you. Good point. That's exactly why I put this here. You need to switch to all on this one. The not doesn't work the way that you think. So some rectangles are squares and some triangles are equilateral. What's the negation of that?
All rectangles are not squares.
All rectangles are not squares, or all triangles are not equilateral. That's when this is false. This statement is false if all rectangles are squares, or all rectangles are not squares, then the statement's false. Or if all triangles are not equilateral, then the statement's false. So if one of those two things happens, then the whole statement is false. So that's its negation. Right? Good catch. Some widgets are gadgets and no wiggles or waggles.
Some widgets are not gadgets, and some wiggles are
No,
waggles.
all widgets are not gadgets.
That's what I said.
You said some.
Um,
All widgets are not gadgets. Perfect. Or
all wiggles.
Some
No,
waggles.
some wiggles.
some wiggles are waggles.
Are waggles. Yeah.
Good? Yeah, English is hard. Saying the opposite of a statement, not as trivial as you think it is. Now, logically, what we've been doing is this little theorem right here, distribution rule. Not alpha and beta is logically equivalent to not alpha or not beta. That's what we've been using over and over again here, trying to give you the intuition for it. So now let's just prove this one really quick. Show you how you do proofs in logic. To do proofs in logic, you just use truth tables. So do the truth table to show that this is in fact the case. So if we have alpha, beta, then here we'll put alpha and, we're going to need not alpha, not beta. Not alpha, not beta. Then we'll do alpha and beta. Then we'll do not alpha and beta. And we'll do not alpha or not beta. So we'll do all those. Sheesh is right. Writing two tables can be somewhat tedious, and you're going to have to write a few of them. Alright, so all the possible combinations for alpha and beta are, we can have alpha's true, beta's true, alpha's true, beta's false, alpha's false, beta's true, alpha's false, beta's false. Alright, so read me the value for not alpha.
False, false, true, true.
Perfect. He's just negating whatever we had here, right?
False, true,
False,
false.
true, false, true.
True.
We're anding together these two
True.
values. True and true is,
True.
true and false is,
False.
false and true is,
False.
and finally true.
No, false.
No, false. Good. Alright, now this is just negating this.
Right.
This is alpha and beta, this is just a negation of this. So the negation of this then is
False, false, true, true, true.
false, true, 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 right? Now, finally, this one, we're ORing together not alpha and not beta. We're ORing these two together, right?
Yep.
So false or false is,
False.
false or true is,
True. True. True.
true
True.
and true. Perfect. So notice that no matter what alpha and beta are, this expression and this expression spit out the exact same value. If alpha and beta both are true, then these are both false. If alpha is true, beta is false, they're both true. If beta is false and alpha is true, they're both true. If they're both false, then these are both true. So since these always get the exact same value, no matter what your alpha and beta are, they're logically equivalent.
Can you assume that if alpha and beta are true, then not alpha or not beta is false? Like, can you go back to the original alpha and beta?
Say that again. If not alpha and beta are true,
No, if I'm saying if alpha and beta are true, so see how those are both true?
if alpha and beta are true,
So in any situation, can you conclude that not alpha or not beta is false all the time?
yes. Anytime alpha and beta statements are true, you instantly know that not alpha and beta is false, or that not alpha or not beta is false. And these say the exact same thing. Since these spit out the same values no matter what the inputs, no matter the truth or falsity of alpha and beta, since this expression and this expression spit out the same value, they're really somehow the same expression. It's kind of like this. If I give you 2x over 4, and I give you x over 2, no matter what number you spit out, you plug in, these always spit out the same value. And so these are equivalent expressions. And so they're equal to each other. Similarly, these are equivalent expressions. No matter what values you plug in for alpha and beta, they always spit out the same thing. Two ways of writing the same thing. That's what we mean by logically equivalent. Any questions on that? Okay, next one. This time we're going to try negating a disjunction instead of negating a conjunction. So, negating a disjunction. I will study hard or I will fail. What's the negation of that? Someone says, I will study hard or I will fail, and I tell you that's not true. What am I saying?
I won't study hard and I will pass.
Right. If I tell you, you'll study harder, you will fail, and you say, nope, watch me. What are you going to do? You're not going to study hard, and you're still going to pass. So it's not this and not this. Right?
Yeah.
Are you missing anybody?
Don't think so.
Okay.
All right. Let's try the next one. Some will work or all will starve. What's the negation of that?
And some won't starve.
The negation of some will work or all will starve is what?
All won't work and some won't starve.
Right. The negation of that is no one will work or all won't work. All won't work and some won't starve. Right?
Yeah. Sounds weird, but it's right.
Yeah.
Some will work or all will starve. The negation of that is no one will work and all will not starve.
No one will starve.
Or not all will starve. Not no one.
Some,
Yeah, right.
Some won't starve.
So a statement saying someone has to work or everyone's going to starve. You're saying no, no one can work and some of us will still live. Bunch of cannibals. Right? Alright. Every triangle is isosceles or every triangle is right.
Some triangles are not isosceles.
And some triangles.
But some triangles are not right.
That's right. That's exactly right. Perfect. No roses are red or some violets are blue.
Some roses are red. Some
And
roses
not all violets are
and no red and violets.
And no violets are blue. Following that? Alright, perfect. Learning how to negate these things, and the rule that we were using there is not alpha or beta is the same thing as not alpha and not beta. So let's write that one out. It's almost going to be the same truth table. We just got to switch this to an or, switch this to an or, and switch this to an and erase the values for those columns and refill them out. So redo that, and redo that. So here we're oring together alpha and beta, right?
True.
So true,
False.
oring together.
Oh, orange.
True or false is
True.
true. False or true is
True.
false or false is
False.
perfect. Now we're going to negate this. So that's just going to be false, 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 true, right? Now this over here, we're anding together these two. Not alpha and not beta. So false and false is
False.
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 False and true is false. True and false is false. True and true is
True.
And then notice that this column and this column are identical. Therefore, these expressions are logically equivalent. Perfect. All right. Proofs. What do we mean by proofs?
Proving something.
Yeah. So when we try to convince someone of the validity of some statement, we say this is true because that is true. If they agree that the that is true, and they agree that the this necessarily follows, then they will be convinced.
False.
If I say, you were at the party last week, and you say, no, I was not at the party because I was out of town. That proves that you weren't at the party. If you were out of town, and we accept that being out of town means you couldn't have been at the party,
What if the party was out of town?
then you would accept that as a proof.
Party's in town.
Right? The party here in the classroom. Right? So that's how you can prove that you weren't at the party. Prove in loose speech, not mathematical proof. Right? That's what it means to prove something. It means justify the statement in a way that we agree that one statement being true implies the other is true. On the other hand, if I said that you were at the party and you said, no, I wasn't at the party because the sky's blue, that doesn't prove that you weren't at the party.
I'm convinced.
Unless someone believes it.
Huh? Alright, yeah, right. The this in that case wouldn't necessarily follow. It doesn't necessarily follow that because the sky's blue, you weren't at the party. It does necessarily follow that if you were out of town, then you weren't at the party. So it's putting them together in this way. So once again, what do we mean when we prove something? When we try to convince someone of the validity of some statement, we say that this is true because that is true. Where if they agree that that is true, that you were out of town, then they necessarily agree that this is true, you weren't at the party. Okay. So logic can be summarized then as a study of the rules for making correct statements. Given statements, how can we make new correct statements from those statements? That's what we're doing, over and over again. So proofs. Proofs always consist of statements of the form, if so-and-so, then such and such. Must also be true. If so-and-so is true, then such and such must also be true. And they can always be phrased in that form. Every single proof in math. So let's do some examples. If 3x equals 4, then x equals 4/3. You're actually doing little proofs when you solve algebra problems. When they say solve for x, what you're really doing is you're showing that if 3x equals 4, then x is equal to 4/3. That's what you're doing. You do little proofs over and over again. They just don't tell you that. Another one. If a equals 2 and b equals 3, then alpha squared plus a times b, or a squared plus a times b is equal to 10. Can be phrased in if-then statements. All mathematical proofs are of the form if alpha then beta. We call alpha here the antecedent or the condition, and we call beta the conclusion. So now let's get into implications. Hardest ones to get. All right. If alpha and beta are statements, then the new statement, alpha implies beta, is called an implication. We also say if alpha then beta, beta if alpha, alpha only if beta, alpha is a sufficient condition for beta, and beta is a necessary condition for alpha. Those are all different ways of saying alpha implies beta. Right? Let's say each of these with some statements. So let's pick an alpha and a beta and say each one of these to help us see how that's the case. Alpha implies beta. So we'll make alpha be there is fire. And we'll make beta be there is oxygen. Right? So there being fire, there is fire, implies there is oxygen. Right? You can't have fire without oxygen. All right, let's read the next one. If there is fire, then there is oxygen. See how that's saying the same thing?
Yeah.
There is oxygen if there is fire.
Yeah.
There is oxygen if there is fire.
Yeah, okay.
All right. There is fire only if there is oxygen. There being fire, we have to say it a little bit different to make it work here. There being fire is a sufficient condition for there being oxygen. And finally, there being oxygen is a necessary condition for there being fire. Or the way you always hear it is, oxygen is necessary for combustion. Something like that, right? Notation, we write alpha implies beta as alpha arrow beta. So implies is represented with a little arrow. So let's do a quick exercise. Restate each of these in the following form, if alpha then beta. And we'll just go down the row like this. So restate that as an if then.
Me?
Yeah,
If I eat strawberries, then I get hydrogen.
perfect. Next.
Let me read it. If people don't study mathematics, then they don't have good sense.
Perfect.
They don't have good sense.
If we have rain this week, then the crops will be saved.
If we have rain this week, then the crops will be saved. Perfect.
If the crop, if if it will rain tomorrow, then it will get cold.
Then it got cold.
Then it gets cold.
Yeah, all right. That works pretty good. Back to you, Hayden.
If there's oxygen, then there's fire. No.
Other way, right?
If there's fire, then there's oxygen.
Perfect.
If there's fire, then there's oxygen.
You sure?
Yeah.
Okay. Not a very good yeah for being sure. Yes, you're right. See, if you would have said yes, I'd believe it. But you said yeah. So, yeah, not trivial converting these, but gotta get used to it. All right. We won't bother going that much depth into these exercises. But we do need to talk about vacuously true. Okay. So we're going to do the truth table for alpha implies beta. And talk about vacuously true at the same time. So alpha implies beta. So we've got our alpha here. We've got our beta. Then we've got alpha implies beta. And we have four possible combinations. True, true. True, false. False, true. False, false. We'll make alpha, Donnie's holding a chalk, and we'll make beta, Donnie's holding a marker. And try and make this quick with our intuition. All right. If Donnie's holding chalk, then Donnie's holding a marker. True, right?
False.
If Donnie's holding chalk, then Donnie's holding a marker.
False.
False. If Donnie's holding chalk, then Donnie's holding a marker.
False.
True, false. Here's the way I help it quick with my intuition. Is the statement false? Is it false that if I'm holding chalk, then I'm holding a marker? It's not false. And if it's not false, what does it have to be?
True.
True. So it feels a little bit awkward calling that true, because I'm not holding a chalk, but you can't call it false. It's not false. So if it's not false, it's true. Finally, if I'm holding a chalk, then I'm holding a marker.
True.
True. Now the other way that we call these two true here, where I wasn't holding a chalk, we call these ones vacuously true. We call it vacuously true because there are no cases to check. If I'm not holding a piece of chalk, there's no case to check. And so we call these two vacuously true. If your antecedent is false, the alpha part, if your antecedent is false, your implication is true. Give me another example that's vacuously true. If I start this, let me just give you one. If Donnie's a purple elephant and the sun is made out of Swiss cheese, true or false?
True.
That's true. It's vacuously true. Because Donnie is not a purple elephant. Maybe. Maybe it's false. I am a purple elephant in disguise. So that's what we mean by vacuously true. So vacuously true. An implication is vacuously true provided that the antecedent cannot be satisfied. If the antecedent is false, the statement is vacuously true. Make sense?
Yes.
Okay. Now the converse of an implication. We call beta implies alpha the converse of alpha implies beta. Now the converse does not say the same thing. It's a different implication altogether. So let's do some examples and talk about if they're true or false to begin with, maybe. So first off, true or false. If an animal is a man, then it is a human being. Is that true?
No.
Not all men are human beings?
That is true.
What's a man that's not a human being?
That animal.
If an animal is a man, what's a man?
I know.
It's an adult human male.
I was thinking male.
Okay. Oh, you're thinking male. Okay. Yeah. No. A man is an adult human male, right? So if an animal is a man, then it is a human being.
Yes.
Okay. Now state the converse of this.
If an animal is a human being, then it is a man.
Perfect. So that's the converse. Now is the converse true?
No.
No, because it can be a woman. Right?
Oh yeah.
Good? Right. So we're stating, so the statements are written alpha implies beta. We're going to reword them as beta implies alpha and see if they're still true. Or still false, depending on the truth or falsity before.
So is if an animal is a sentence addition?
It's the
Why are we not switching if an animal is?
It's the
So
Oh, sorry.
this is if an animal is a man, then it is a human being. So here's our alpha, here's our beta, right?
So why would we do?
So the converse of that is if
Oh, it is. Yeah.
if it is a human being, being the
I
animal,
see that.
then it is a man. Okay, good?
Yep.
So every man born in India is an American citizen.
Every.
Indiana, not,
Yeah.
not India. Indiana.
That's not true.
Every man born in Indiana is an American citizen.
If you are
True.
That's not true.
not
American,
the girls,
if,
just the guys.
Whoa.
Is every man born in Indiana an American citizen?
No.
Not if they're
So
born there and
Indiana
moved to
is a
India.
state.
Oh. Did they start out an American citizen?
That's true.
Indiana.
We're assuming
He's saying
you're not
Indiana.
changing your residency throughout the course of your life. Alright?
Okay.
All borders are blocked. Okay. So every man born in Indiana is an American citizen at some point in their life. Okay.
Yep.
Now, what's the converse of that?
Every American citizen born in Indiana.
Perfect. And is that true?
Wait,
No.
not
No.
quite. Because he said every American citizen. He didn't say every American citizen that is a man.
Yeah. That's fine. Good enough. Alright. Let's do another one. If x minus y equals 3, then x is greater than y.
If
True.
X.
If x minus y is 3, which of these numbers are bigger? X.
6.
If you have x pizzas, and I take away y of them, and you're left with 3, did I take away more pizzas than you have?
Yes.
No. Because you still have 3.
Yes.
Okay, so if x minus y equals 3, then x is greater than y.
If
That's
X
true.
is greater than Y, then X minus Y equals 3.
Perfect, which is false, right? The point of these exercises is you're going to be tempted to get confused that when you have an implication, its converse is also the case. One of the most common fallacies in logic is people making that exact assumption. Happens all the time. All right. If plants are green, they must have sunshine.
True.
False.
If plants are green, they must have sunshine. I'm
Sure.
guessing it still does. I'm guessing
Underwater.
Dude.
green means chlorophyll means it's
Photosynthesis.
somehow using photosynthesis.
Yeah.
I'm assuming it's
Plants are
true.
green.
I'm not positive on this. We'll pretend it's true.
Slime in caves.
If plants are green, then they must have sunshine. We'll pretend it's true. If a plant must have sunshine, then it's green, would be the converse, which obviously is false, right? Finally, if 2 plus 4 equals 5, then 4 plus 7 equals 10.
True.
Is that true?
Yeah. Yeah.
Vacuously.
It's vacuously true. Wonderful. If some false statement, then some false statement is true. False implies false is true. Vacuously true. And what's the converse of this?
If 4 plus 7 equals 10, then 2 plus 4 equals 5.
And is that true?
Yes.
Still
Yes,
Vacuous.
still true. Wonderful. Getting a good feel for all these. All right. So we had the converse of an implication, which does not say the same thing. Now we're going to talk about the contrapositive of an implication, which does say the same thing. What's contrapositive? The contrapositive of alpha implies beta is not beta implies not alpha. Those actually say the exact same thing. As weird as that is. Let's do the truth table for that really quick. alpha beta. I'll do the not beta first just to help us in ordering, and then not alpha. And then we'll do alpha implies beta. And then we'll do not beta implies not alpha. Alright, so our possible combinations are true, 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 false, false, true, false, false. Not beta then is going to be false, true, right? Just negating this.
Yeah.
Not alpha
False,
is going
false,
to be
true, true.
false, false, true, true. Perfect. Alpha implies beta. True implies true is.
True.
True implies false is. False implies true is.
True.
False implies false is.
True.
Perfect. And then not beta implies not alpha. False implies false is.
True.
True implies false is.
False. True.
False.
False.
Right? True implies false is false. True implies true is.
True.
And true implies true is.
True.
And there you go. Notice true, false, true, 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 false, true, true.
Oh, that was funny.
Did I do something weird?
Yeah.
You switch from not A and
You went from
A
not
implies
beta to not beta and not alpha to alpha implies beta.
Oh, oops.
You're comparing those two.
I wasn't comparing these two.
Yeah, you switch them over to.
Okay, I see. Yeah. Sorry about that. We still got the right numbers though, right?
Yeah.
False implies true is true, true implies true is true. Okay. Good catch. And there we go, they're logically equivalent. And it's one thing to see the proof, it's another thing to make it appeal to your intuition. So let's try to make it appeal to your intuition. First, let's start with a simple one. If Donnie's wearing shoes, then Donnie's wearing socks. Right? We'll assume that's true. We'll assume every time I wear shoes, I wear socks underneath. Pretty standard. So if Donnie's wearing shoes, then Donnie's wearing socks. State the contrapositive of that. If I'm not wearing socks, then I'm for sure not wearing shoes. If you know that every time I wear shoes, then I'm wearing socks, then you also know anytime I'm not wearing socks, I'm not wearing shoes. They'll say the same thing, right?
Right.
So let's do some. X equals 3 implies x squared equals 9, right? If x equals 3, then x squared equals 9. What's the contrapositive of that?
X squared is not equal to 9, then x
Perfect.
is not equal to
You also know if x squared is not equal to 9, then you know that x is not equal to 3. Right? Let's try another one. If two lines intersect, then they are not parallel.
3. Two lines do not intersect, and they are parallel.
If two lines are not parallel.
Careful.
If two lines are parallel, then they do not intersect.
Right. If two lines are parallel, then they do not intersect. Here's our alpha, here's our beta. Alpha implies beta is the same thing as not beta implies not alpha. So if two lines intersect, then they are not parallel, is the same thing as if two lines are parallel, then they do not intersect. Just a negation of each of those, right? Okay, let's do another one. If food is sweet, then it has honey in it.
If food does not have honey in it, then it's not sweet.
Perfect. Obviously not true, but that is contrapositive. If there is no atmosphere on Mars, then there is no life there.
If there's life on if there's life on Mars, then there's an atmosphere.
Perfect. Follow that? Finally, oxygen is a necessary condition for fire. First off, which one is that saying? If oxygen is a necessary condition for fire, state that in an if-then first.
If there's fire, and there's oxygen.
Right, so here's your alpha. There's fire. This is the alpha. And this right here is the beta. We're saying this says alpha implies beta. Oxygen is a necessary condition for fire, means if there's fire, then there's oxygen.
Which means if there's no oxygen, then there's no fire.
Which means if there's no oxygen, then there's no fire. Perfect. Good?
Yep.
All right. Oh, logical equivalence. So that ends implication. That's the hardest one. Logical equivalence is probably the easiest one. So, if with two f's, you're going to see this all the time in mathematics, we use it left and right. If with two f's, is an if and only if. We'll just read what it says. Observe that alpha if beta is the same thing as beta implies alpha. You see that? Alpha if beta means if beta, then alpha. You'll get paid if you work today. Means if you work today, then you'll get paid. So this is saying beta implies alpha. Right? Now, alpha only if beta is saying alpha implies beta. There's fire only if there's oxygen. Means if there's fire, then there's oxygen. So alpha if beta means beta implies alpha. Alpha only if beta means alpha implies beta. Beta implies alpha, alpha implies beta. Right? So now, if I say the statement, alpha if and only if beta, then that's saying the same thing as alpha implies beta and beta implies alpha. Both those together. You see that? Since alpha if and only if beta is so frequently used in math, then we just write it as alpha if beta with two f's. So that alpha if beta with two f's means alpha if and only if beta. It means alpha implies beta and beta implies alpha. Good? Okay. And that's what we mean by logical equivalence. So we call the two statements alpha and beta logically equivalent, provided that you have alpha if and only if beta. So here's our last truth table that we're going to do. So we'll write it out. Alpha, beta, alpha implies beta, beta implies alpha, and then how do I want to write this one? And then we'll do alpha if and only if beta, which we represent with arrows back and forth like that. Yeah, we'll do that. Okay, so our last truth table here. True, 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 false, false, true, false, false. Okay, true implies true is. True. True implies false is. False implies true is.
True.
False implies false is.
True.
Finally, for this one, we have true implies true is.
True.
False implies true is.
True.
True implies false is.
False.
And false implies false is.
True.
True. Sorry, mess of these. Hard to see where one symbol ends and the other begins. Alright. Anyways, so now, this logical equivalence, this double back and forth arrow, means alpha if and only if beta. So it means alpha implies beta and beta implies alpha. So this is anding together these two columns. That's what it means. So true and true is true. False and true is
False.
true and false is
False.
true and true is true. So notice that alpha if and only if beta is true when alpha and beta have the same value. Where do alpha and beta have the same value? They have the same value right here, and they have the same value right here. That's when alpha if and only if beta is true. And it's false when alpha and beta have two different values. So the other way that we call this operator the logical equivalence operator. It means that the thing on the left side always has the exact same value as the thing on the right side. So it's only true if alpha and beta have the same logical value. Otherwise it's false. Make sense? So that's why it's logical equivalence. Pretty straightforward one. Just means, do those two things have the same value? If they do, it's true. If they have different values, it's false. Okay, perfect. So those are all the operators that we'll see. Finally, the precedence of them, how they apply. It's kind of intuitive from what we've been saying already. But your precedence is your negation, then your and, then your or, then your implies, then your logical equivalence. You know what I mean by precedence?
Order of operations.
Yeah, basically order of operations. When you see something like not alpha or not beta is logically equivalent to not alpha and beta, then you understand that you're applying the not to the alpha before you or it to the thing over here. Right? And then you apply the not over here before you check, do they have the same value? So this kind of acts the same way that equals does in math, or in algebra. The negative here acts a lot like, the negation here acts a lot like a negative sign. So rewriting this is like negative A plus negative B is equal to negative A plus B. It's kind of like that. Not identical, but kind of. Yeah, I know. You switch the signs. It's Boolean algebra up here. But kind of. Anyways, so that's the precedence that you apply these in. Your not has the strongest precedence, then your ands, then your ors, then your implies, then your logical equivalents. And you can usually tell. So let's do a couple examples just to make sure. Alpha implies beta is logically equivalent to not beta implies not alpha. So you naturally know that the nots are applied like that, and then you're comparing this whole expression with this whole expression. Right? We were not saying, for example, we were not saying that alpha implies beta is logically equivalent to this expression. That is not what we were saying. That would be putting the parentheses in the wrong place.
Yep. I see.
That's what I mean by precedence. Oh, I wrote it over there. So this is the same as alpha implies beta is logically equivalent to that, which is exactly what we wrote. Let's do another one. Alpha or beta and not alpha. Where do we put parentheses? Do we put the parentheses around alpha or beta? Or do we put the parentheses around beta and not alpha?
First round not.
Huh?
Yeah.
The and.
And before or.
And before or.
Oh.
So this is the same as rewriting it over there. You do alpha or beta and, I put the not in parentheses in case that one wasn't obvious, but I think you kind of get it. The way we think about it is negation acts a lot like minus, and acts a lot like times, or acts a lot like plus. We don't really have a good one for implies, and then this acts a lot like equals. Just to help you keep it straight in your head. But you'll get used to these things the more you use them. And so that's logical equivalence. And that's it for propositional logic. Okay. So that's it for material that we have to cover today. We did a much deeper dive into logic and what a proof is than your book actually does. So I know that that felt like a lot. You had a lot dumped on you. Don't worry, we're going to cover all that again. I'm giving you the full thing now instead of how the author does it. He tries to give you a little bit, then the full thing. I just give you the full thing, and then when we cover it again, the second time through, you'll really get it. So that's sections 4 and 5, which is all we have to cover today. So you can do a break, and then you have the rest of class for homework or questions or anything like that.
Yes.